Welcome back. So today we'll be continuing with another example showing how to use the Raspberry Pi's GPIO pins in Python, and we'll be also going over some important information regarding the latest Raspberry Pi 5 and its GPIO pins. Now in my previous video I said I'd also be showing some examples using an ultrasonic distance sensor and an IMU, but I decided to push that back to my next video. The reason for this is because I don't want this video to be excessively long, and I think it's better to keep most videos down to a more digestible length. So again, if you're interested in seeing how to use these sensors, just bear with me and I'll definitely be getting into those in my next video. So let's first do a quick recap of what I've already covered in regards to GPIO pins. In my previous video, I gave a high-level overview of all the different communication protocols and peripherals that are available through the Raspberry Pi's GPIO header, and other SBCs and microcontrollers as well. And in another video, I also showed how to make a simple Python program to control the output pins and connect one of them to a simple transistor circuit to control LEDs, but I didn't show how to use the input pins. So today's video will pick up where that one left off and will show how to use the input pins with a simple push button example. Even though this video will focus on the software side of things, it still involves some knowledge of circuits as well. So if you're not familiar with some of the circuits related concepts in this video, then you should definitely watch my playlist titled Practical Circuits and Electronics 101. These videos go over the fundamentals of electrical engineering with a focus on using this knowledge for practical projects. The playlist currently has 10 videos, but I'm planning to add several more later this year, so stay tuned for that. Now let's head over to my website and go to the GPIO Python guide, which I've recently updated to include today's examples and several more that I'll cover in my next video. The link to the written guide is in the video description. So let's first start with the Raspberry Pi 5 and what you need to know if you own one. As you can see here, I finally purchased a Model 5 for myself, and overall, I like it a lot. It's much faster than the previous generations and I'm excited to use it in future projects. But something that's a little annoying is that they created a new chipset to handle all the GPIO functions, which means all the old GPIO libraries need to be updated to keep compatibility with the Pi 5. Unfortunately, the RPi GPIO library that I used in the previous video is not compatible with the Pi 5, but luckily there's another library that is compatible, called RPi LGPIO, and it's a drop-in replacement for the older library, which means it supports the exact same Python programs. This library is also compatible with all the previous Pi models as well, so generally speaking it's probably a better choice. If you previously installed the old library and want to use the new one, make sure you uninstall the old one first before installing the new one. It can be installed with this command here. And if you haven't already given your user access to the GPIO pins, make sure you do that and restart before continuing. Now let's scroll down. This is the test code I used in the previous video, so let's skip it and continue down. Now, in the previous video, I also covered how to use the remote GPIO library so that you can control the Pi's pins from a separate computer connected to your network. But unfortunately, this isn't compatible with the Pi 5 either. There appears to be an alternative remote library for the Pi 5, but its functionality is pretty basic and not as robust as the previous library was. So hopefully this continues to get developed since remote GPIO is a pretty useful feature. But anyway, we won't be using the remote library in this video, so let's go down to the input section, which has today's example. So let's first review the circuit for our push button and LED. On the right hand side is our transistor and LED circuit, and this is exactly the same as the previous video. So if you want details on this part, then check out that video and my Electronics 101 video on transistors. So let's now look at the left side of the circuit with the push button. You'll notice one side of the button is connected to the 5-volt rail and the other side is connected to a voltage divider, which is then connected to our Pi's input pin. When the button is pressed, it creates a short which allows the current to flow through to the other side. The reason why we have a voltage divider is because the Pi's pins are only rated for 3.3 volts, so we need to reduce the voltage going into it when the button is pressed. As you recall from my Electronics 101 videos, this is the equation for a voltage divider. Plugging in these resistor values with 5 volts gives us roughly 3 volts output, which is a good value for the Pi's pins. Keep in mind you don't need to use these exact resistor values as long as they have the same ratio. So for example, you could use a 680 ohm resistor for R3 and a 1K resistor for R4. But generally speaking, I wouldn't use values that are less than a few hundred ohms, and likewise, I wouldn't go too high either. I'd keep the resistor values below 100K. The advantage of using higher value resistors is that the circuit will consume less current, which is good for battery powered devices. But going too high can lead to other issues, so again, I wouldn't use values greater than 100K. But now some of you might be thinking, what if we simply use the 3.3 volt rail instead of the 5 volt rail? Would you still need the voltage divider? Well, the answer is no, you don't need the voltage divider, but you'd still want to keep the R3 resistor. The reason for this is, let's imagine you accidentally set this pin as an output instead of an input, and then you push the button. Without the resistor, this would create a short circuit, which, as we all know, is really bad and can lead to damaged equipment. So, just to be extra safe, you'd want to include this resistor here to limit the current in that situation. So now let's move on to the code. I'll quickly explain what the code is doing before we run it. The top half here is the same as the previous example, except now we're adding the input pin. I'm using pin 8 as the output and pin 10 as the input. But again, you can use any of the GPIO pins listed here. All you need to do is specify them here. Also, remember that the numbering scheme used will depend on what you enter in the set mode function. Since I use the GPIO.board setting, the program will use this pin numbering scheme here. But you also have the option of using GPIO.bcm in the set mode function, which means you'll then need to use the GPIO numbering scheme instead. So feel free to use whichever scheme and pins you want. Now let's look at the main loop. This if statement here checks if the input is being pressed. If it's not being pressed, it will skip down to the sleep function, which is set for 1/10 of a second, and then go back to the top and check again, and we'll repeat this process until you press the button. When the button is pressed, it will run the following code. First, it will turn on the output pin which controls our LED. Then it will print a message to the terminal saying button pressed. Now this next while loop will stay stuck in the loop doing nothing as long as the button remains pressed. When you release the button, it will break out of this while loop and continue to the next line, where it will set the output pin to off, which will turn off our LED. Then it will sleep and start the process all over again, waiting for you to press the button again. Now these sleep functions actually aren't necessary, but without it, the program will run as fast as possible, which means one of the CPU cores will get maxed out for no real reason. For our purposes, we don't need to run this loop as fast as possible, and putting this sleep function will dramatically reduce CPU usage. I set the sleep function to only 1/10 of a second, which is fast enough that you won't really notice the lag. But you can set this lower if you want a faster reaction time. For this application, it's not necessary to run it any faster, but there might be some applications where you'd want a faster reaction time than 1/10 of a second. But again, the trade-off is higher CPU usage. So now let's run the program. Like I've shown before, after logging into the Raspberry Pi, you can simply enter nano at the command line, name your Python file, and then paste the code into this window and save it. But the Nano editor is extremely basic and is difficult to edit in. So instead, I'll do an SFTP connection into my Pi so that I can create and modify files from my desktop PC's editor or IDE. I showed how to do SFTP connections in my Diet Pi Part 2 video. So check that out if you want to learn how to do an SFTP connection. Now, I've already connected to my Pi here, so now I'll simply create a new file and name it button.py. Now I'll open it in my editor, copy and paste the code, and then save the file. Next, I'll head back to my SSH session on the Pi and run the program. And as you can see, whenever I push the button, the light turns on, and it stays on as long as I hold down the button. And when I release the button, the light turns off. Of course, this is a simple example and is somewhat trivial since we actually don't need a Raspberry Pi to get this functionality. We could have just wired the push button directly to the base of the transistor and it would do the same thing. But the point here is to give a straightforward example showing how to use the input pins. You can use this code as the basis for other applications and replace the LED parts of the code with any other functionality you want. For example, I previously did a video explaining how the code works for my YOLO Smart Security Camera application. This command here sets up the parameters for FFmpeg, and then it calls this function which actually starts the recording. Well, if you wanted to, you could copy and paste this code into the push button example we just did, and then you'd have a program that records a video stream whenever the button is pressed. Or let's say you wanted to start a recording in OBS whenever the button is pushed. This is completely possible since OBS allows you to easily run your own scripts in the tools section here. Or perhaps you want to create your own game and want to use a custom-built controller. This code can be easily integrated into your game's code, or any other application you can think of. Also, you're not just limited to push buttons. You could replace the push button with an on-off switch like this one here. When the switch is flipped, it creates a short between the two pins just like the push button does. So you wouldn't need to change the code or anything if you wanted to use a switch instead. And of course, there's a number of other things you can use input pins for other than just buttons and switches, including interfacing with other components and with sensors. But anyway, that's all for today. I know today's example was relatively simple, but I want to make sure we cover the fundamentals before we move on to more advanced stuff. Like I mentioned earlier, stay tuned for my next video where I'll show how to use various sensors in Python, including an ultrasonic distance sensor and an IMU. If you enjoyed this video, then be sure to give it a thumbs up and also subscribe to the channel if you haven't already. As always, thanks for watching and I'll see you next time.